Welcome to our show. Today, we're diving into the fascinating world of early rocketry and space exploration. We have an expert with us who's going to take us on a journey through the pioneering days of rocket science. So let's start with the visionary who kicked it all off. Can you tell us about Konstantin Tsiolkovsky?
Absolutely. Konstantin Tsiolkovsky was a remarkable figure in the history of rocketry. He was a self-taught visionary with a wealth of innovative ideas. Despite lacking a formal academic background, he was undeniably a pioneer in the field. In the late 19th century, Tsiolkovsky spent years pondering how humans could escape Earth's gravity and venture into outer space.
Wow, that's quite impressive for someone without formal training. What inspired him to think about space travel?
Interestingly, Tsiolkovsky was greatly influenced by science fiction, particularly the work of French author Jules Verne. Verne's 1865 novel, From the Earth to the Moon, and its sequel, Around the Moon, captured Tsiolkovsky's imagination. However, he realized that Verne's idea of using a giant cannon to launch people to the moon wasn't practical. The acceleration would be too intense for humans to survive.
So what was Tsiolkovsky's solution to this problem?
Tsiolkovsky proposed using rockets instead. He understood that rockets could provide slow and steady acceleration, which would be much more suitable for human space travel. He even wrote his own science fiction novel called Beyond the Earth, where he detailed how rockets could be used for interplanetary travel. In this book, he described fascinating scenes near the moon and asteroids and even proposed the idea of a space city.
A space city? That sounds like something straight out of a modern sci-fi movie. What did he envision for this space city?
It was indeed quite futuristic. Tsiolkovsky suggested that this space station should be circular and rotating to create artificial gravity. This concept of a ring-shaped space station was first envisioned by him, demonstrating how thoroughly he considered various aspects of space travel. It's remarkable how many of his ideas have influenced modern space exploration.
That's incredible foresight. Did Tsiolkovsky's novel include any other interesting details?
Yes, it did. In his novel, Tsiolkovsky imagined a palace in the Himalayas inhabited by super-wealthy individuals, including famous scientists like Galileo, Newton, Laplace, and Helmholtz. They were led by a Russian character named Ivanov. While his character development might not have been the strongest, it's a common issue in hard science fiction where the focus is more on the scientific concepts.
Fascinating. Now let's shift gears a bit. Can you tell us about the state of rocket technology during Tsiolkovsky's time?
Certainly, at that time, rockets were primarily used as weapons on the battlefield or as fireworks for celebrations. No one could have imagined how far rocket technology would advance. Many children, including myself, enjoyed playing with small rockets during festivals. The simplest form was a firework known as a sky chaser or bottle rocket.
Oh, I remember those. Did you ever experiment with them?
I did, actually. As a child, I used to place these rockets in metal tubes and launch them from my shoulder, similar to how modern shoulder-fired missiles are launched. This improvised launch tube improved accuracy significantly. We even had playful firework battles with friends. But I should emphasize that children should never play with such dangerous items.
That sounds both exciting and dangerous. Did you learn anything from these childhood experiments?
Absolutely. We quickly realized that achieving greater heights with rockets isn't simply a matter of using more propellant. If the propulsion efficiency is low, even large amounts of fuel won't result in significant altitude gains. This principle was something Tsiolkovsky also recognized, but he took his research much further.
Speaking of Tsiolkovsky's research, I've heard about something called the rocket equation. Can you explain what that is?
Of course. In 1903, Tsiolkovsky published a paper titled Exploring Space Using Jet Propulsion Devices in the Science Review Journal. In this paper, he derived the rocket equation, which describes the relationship between a rocket's final velocity, its exhaust velocity, and the ratio of its initial to final mass. It's a fundamental equation in rocketry.
That sounds pretty technical. Was Tsiolkovsky the first to discover this equation?
Actually, it's an interesting story. The equation was discovered earlier in 1813 by a British scientist named Moore, but it was kept as a military secret by the Royal Military Academy. so the credit for this equation still goes to Tsiolkovsky, who derived it independently.
Fascinating. What was Tsiolkovsky trying to achieve with this equation?
Tsiolkovsky's primary concern was whether a rocket could achieve a velocity of 8 kilometers per second, which is slightly more than what we call the first cosmic velocity or orbital velocity. This speed, approximately 7.9 kilometers per second, is the velocity required for an object to orbit Earth at its surface, ignoring air resistance. At this speed, an object would complete one orbit in about 85 minutes.
That's incredibly fast. Is this the speed at which satellites and space stations orbit Earth?
Not quite. That 85-minute period represents the absolute minimum time for any satellite or space station to circle the Earth. In reality, satellites and space stations orbit at higher altitudes and thus have longer orbital periods. Typically, objects in Earth orbit take around 100 minutes to complete one revolution.
I see. So what factors determine a rocket's ability to achieve these speeds?
Great question. There are two crucial factors. One is the mass ratio, which is the relationship between a rocket's initial mass, when fully fueled, and its final mass, after all fuel is burned. A higher mass ratio is better for rocket performance. The other vital factor is the exhaust velocity of the rocket. Higher exhaust velocities lead to better performance.
That makes sense. How do engineers deal with these factors?
Engineers go to great lengths to reduce the structural weight of rockets, sometimes using materials as thin as a soda can, but made of stronger alloys like titanium. Some rockets even use high-pressure helium gas inside to maintain their shape despite the thin walls. As for improving exhaust velocity, this is why Tsiolkovsky proposed using liquid fuels for rockets, as they offer superior performance compared to solid fuels like gunpowder.
Interesting. Can you explain the difference between liquid and solid fuels in rockets?
Certainly. Liquid fuel engines offer significant advantages over solid fuel rockets. While solid rockets produce exhaust containing solid particles like aluminum oxide, which can't expand to produce work, liquid fuel engines primarily generate gaseous exhaust products. This allows for more efficient energy conversion and higher exhaust velocities.
That's fascinating. Did Tsiolkovsky anticipate any of the engineering challenges that come with liquid fuel rockets?
He did, and he even proposed some clever solutions. For example, he understood that rocket nozzles would need to withstand extremely high temperatures. His solution was a double-walled nozzle design where the fuel would first flow through the nozzle's outer layer, cooling the nozzle while simultaneously preheating the fuel. It's an ingenious approach that serves two purposes at once.
That's brilliant. Are there any other advantages to liquid fuel rockets?
Yes, liquid fuel rockets offer more flexibility in their operation. Engineers can use pumps to pressurize the fuel, preheat it before combustion, and employ various other techniques to enhance performance. These options aren't available with solid fuel rockets, which rely solely on the combustion of their premixed propellants.
It sounds like liquid fuel rockets are superior in every way. Is that the case?
Not exactly. Different types of rocket engines have their own strengths and weaknesses. For example, Tsiolkovsky also envisioned electric propulsion systems, which we now call ion engines. These engines use electromagnetic fields to accelerate charged particles to very high speeds, resulting in excellent efficiency. Modern ion engines can operate for years on a small amount of fuel, slowly but steadily accelerating spacecraft to incredible velocities.
That sounds amazing. Why don't we use ion engines for all space travel then?
The downside of ion engines is their extremely low thrust. They're often jokingly referred to as having the power of a mouse's sneeze, barely enough to blow a piece of paper. While they're great for long-term acceleration in space, ion engines can't overcome Earth's gravity to launch a rocket. On the other hand, solid fuel rockets, despite their lower efficiency, provide enormous thrust. This makes them ideal for use near the Earth's surface and at low speeds, such as during the initial stages of a launch.
I see. So each type of engine has its place. Did Tsiolkovsky consider other aspects of space travel beyond just getting into space?
Absolutely. Tsiolkovsky's vision extended beyond Earthbound rocketry to interplanetary travel. He recognized that spacecraft would need to decelerate when entering the atmospheres of other planets. His solution was to use atmospheric friction to slow down the spacecraft, converting its kinetic and potential energy into heat. This process would generate enormous temperatures, and Tsiolkovsky proposed using liquid nitrogen for cooling. While we now know this specific method isn't feasible, his foresight in considering the entire journey, including re-entry and landing, was remarkable for his time.
That's incredible foresight. How was Tsiolkovsky's work received during his lifetime?
Unfortunately, Tsiolkovsky's work was largely ignored during the Tsarist era. However, after the October Revolution, he gained recognition from the new Soviet leadership. In 1920, Lenin personally ordered support for Tsiolkovsky's rocket research, providing him with housing and membership in the Soviet Academy of Sciences. By this time, Tsiolkovsky was elderly and requested to focus solely on rocket research. The Soviet government granted him a lifetime pension, allowing him to dedicate himself to his studies.
That's quite a turnaround in his fortunes. Did this support lead to more breakthroughs?
Indeed it did. In 1929, Tsiolkovsky published a paper on rocket trains, introducing the concept of multi-stage rockets. He explained that discarding empty fuel tanks and engines as the rocket ascended would be more efficient than carrying them for the entire journey. While the reality is more complex, as each stage requires its own engines, this idea formed the basis for modern rocket design.
That's a concept we still use today, right? Did Tsiolkovsky have any other ideas that were ahead of his time?
Yes, he did. Tsiolkovsky also proposed the concept of parallel staging, where multiple rockets would be bundled together. All engines would fire at launch, and as fuel was depleted, it would be transferred to a central core before discarding the empty outer rockets. Although this exact method isn't used today due to its complexity, it demonstrates Tsiolkovsky's thorough approach to problem-solving in rocketry.
It sounds like some of Tsiolkovsky's ideas were a bit too complex for practical use. Can you give an example?
Certainly. While Tsiolkovsky's idea of transferring fuel between rockets mid-flight was innovative, it proved impractical in real-world applications. For example, the Long March 5 rocket, nicknamed Fat 5, uses different types of fuel for its core stage and boosters. The central stage employs liquid hydrogen and liquid oxygen engines, while the four surrounding boosters use liquid oxygen and kerosene engines. These fuels are not interchangeable, making mid-flight fuel transfer unfeasible.
I see. Despite these impracticalities, it seems Tsiolkovsky's work was foundational to modern rocketry. How is he remembered today?
Tsiolkovsky is widely recognized as a pioneer of space exploration. His famous quote, "Earth is the cradle of humanity, but one cannot remain in the cradle forever," encapsulates the dream of venturing beyond our planet. Although Tsiolkovsky never built or tested a rocket himself, his blueprints laid the foundation for future rocket development. At the age of 75, he received the Order of the Red Banner of Labor for his contributions. However, he passed away in 1935 before witnessing the realization of his dream of rockets reaching space.
That's a bit sad that he never got to see his ideas come to fruition. What happened to rocket development after Tsiolkovsky?
Well, it's an interesting story. During the period of the Great Purge in the Soviet Union, some imprisoned individuals continued to work on rocket designs. This unusual circumstance led to the Soviet rocket program essentially beginning in prisons. Meanwhile, in other parts of the world, practical-minded individuals were eager to tackle the challenges hands-on.
That's quite a twist. Who were some of these practical-minded individuals?
One of the most notable was Robert Goddard, an American professor from Massachusetts. Just as Jules Verne had inspired Tsiolkovsky, H.G. Wells greatly influenced Goddard. Wells' science fiction novel, The War of the Worlds, sparked Goddard's lifelong fascination with outer space when he was 16 years old.
It's interesting how science fiction seems to have inspired so many early rocket pioneers. What contributions did Goddard make to rocketry?
Goddard made several important contributions. In 1907, he wrote a paper describing how gyroscopes could be used to control aircraft attitude. This insight proved to be crucial, as both airplanes and rockets now rely on gyroscopic control systems. He also conducted numerous rocket experiments, though these often proved challenging to carry out on a university campus due to the explosions, fires, and smoke they produced.
I can imagine that would cause some problems. How did Goddard manage to continue his research?
It wasn't easy. Financial constraints posed a significant problem for Goddard. His experiments quickly depleted his salary, forcing him to seek external funding. Eventually, the Smithsonian Institution showed interest in Goddard's work and agreed to provide him with $5,000 for his experiments. In exchange, Goddard produced a manuscript titled A Method of Reaching Extreme Altitudes, which contained all of his preliminary research findings. The Smithsonian published this groundbreaking work on rocketry in 1919.
That must have been exciting for Goddard. How was his work received by the public?
Well, it's quite an interesting story. In 1920, Goddard wrote to the Smithsonian about lunar exploration. The media responded with skepticism, and his ideas received significant coverage in the New York Times. Some critics accused Goddard of misunderstanding Newton's second law, believing that rockets couldn't function in a vacuum.
Oh no, that must have been frustrating for Goddard. Did he ever get vindicated?
He did, but it took a while. 50 years later, the New York Times published a small apology to Goddard, acknowledging their error. It's a reminder of how revolutionary these ideas were at the time and how far we've come in our understanding of space travel.
That's quite a journey from ridicule to recognition. It really puts into perspective how much progress we've made in rocket science and space exploration. Thank you so much for sharing all this fascinating information with us today.
It's been my pleasure. The history of rocketry and space exploration is full of visionaries, challenges, and breakthroughs. From Tsiolkovsky's theoretical work to Goddard's practical experiments, these pioneers laid the groundwork for everything we've achieved in space exploration today. It's a testament to human ingenuity and the power of scientific inquiry.
Absolutely. And it's clear that we owe a great debt to these early pioneers. Their work continues to inspire and guide us as we push further into the frontiers of space. Thank you again for joining us, and to our audience, we hope you've enjoyed this journey through the early days of rocket science.